All right, welcome back to another one. This time we're just gonna go through some example problems of vectors. This is actually the homework from Shrestha, homework 3, and I'm just gonna go through all the problems and show how to solve them, so y'all can get a good idea of like how to apply all the knowledge we talked about in previous videos. So let's start with problem number 1, which is find a dot b. So we're going to find the dot product of b. And finding a dot product, if you remember, is just multiplying the each of the values. So the x value of a times the x value of b, and then adding that to the y values times to each other, the product of the y values. I mean, so the a is, let's see on the screen, 9 comma negative 2. I'm going to dot product of that with b is 3 comma 8. So 9 times 3 is 27 plus negative 2 times 8, negative 16. So 27 minus 16, let's do the math. 27 minus 16 is equal to 11. And as simple as that, that's how you get the dot product. Let's move on to the next problem. Okay, one thing I don't like about this homework is that every single question covers something different, so you don't get to practice by repetition. So you just have to practice the principle. So the next one is find a as a function of b. So this one is essentially the same thing, but it's a bit more complex. Instead of giving us two vector components, we get a bunch of things. And so we get the what is it, the magnitudes of A and B and the angle between them. So how is this possible? Well, let's remember that, well, this formula right here, cosine of theta is equal to A dot B over magnitude of A times the magnitude of B. So what you're going to be able to do is just take the magnitudes, move them to the other side of the equation, and you get magnitude A times magnitude B cosine theta, and then that's going to be equivalent to A dot B. So we don't need to actually go through the function of multiplying the vector components or getting the dot product of components to use the correct terminology. All we have to do is run this equation. So what are our values? So A is equal to 60, I think, so negative. Yeah, it's just 60. B is equal to 70, and our theta, our angle, is equal to 3 pi over 4. Now, if you're confused why an angle can be 3 pi over 4, is because you can, if you remember trigonometry, measure your angles in something called radians, which is like the other version. No, you can measure it in pi, which is called radians. It's a unit that's called radians. So we can look over on the unit circle to see what 3 pi 4 is equal to in terms of, sorry, one microphone just done. In degrees, or we can just calculate like this. So we're going to take, plug in the equation, 60 times 70 times, and we can go look at the unit circle for this. So the cosine value of 3 pi over 4 is negative root 2 over 2. So cosine of 3 pi over 4 is equivalent to negative root 2 over 2. Simple as that. So it's just going to be 60 times 70, which is 4,200, equals 4,200 negative root 2 all over 2. So we're going to just divide that by 2, and we're going to get negative 2,100 root 2, and no denominator, and that'll be our answer. And if you look on the homework, that is the correct answer. I hope that makes a bit of sense. Anyways, moving on to the third problem. This one gets a little more complex if you've never actually like studied it before. Because I was stumped when I first did it. I did a bunch of random mathematical things, went down a bunch of back paths until I figured it out. And it's quite simple. And mostly because in the class we never actually like gave this equation the focus that it needs. Because this equation is fundamental to everything. It's all about cosines. So let's see, the next problem is essentially we're given a triangle made of three vectors. All these vectors are unit vectors and it is an equilateral triangle. And we have vector u, v, and w. Correct? Yep, those are correct. So we can start with moving them around. So we're going to just put them all with the same starting point. So we're just going to take each vector and let's see, vector u kind of goes off in that direction. Vector v kind of goes off in this direction, and vector w goes off in that direction. So it's kind of like a ray. And what else do we know about this? So one, the problem says that each of these are unit vectors. A unit vector, I'm going to write uv, has a magnitude of 1. So what we already know is that each of these has a magnitude of 1. So if we're going to plug it into an equation, we already know that cosine theta is going to be equal to the dot product of A and B. However, we don't have any coordinates to be able to write a component for this. We don't have the exact angles, and I'm sure we could math it out, but what we do have angles. Yeah, so I just got lost on my words because this is exactly where I was going. What else do we know about this triangle or these vectors? They have 60 degrees in between each of them. You see how it's an equilateral triangle? Well, each angle is equal to 60 degrees. That means there's 60 degrees right here, and for u to w, that's 120 degrees. So all I have to do is plug it back into the equation. Cosine theta is, well, let's rewrite it. It's going to be magnitude of A times magnitude of B times cosine theta is equal to A dot B. Or in this case, it's going to be equal to u dot v and u dot w. So what are our angles? Let's come over here. Hey, what's up? A is equal to 1. Well, not A, but u is magnitude of 1, v is a magnitude of 1, and then cosine of 60. So what's cosine of 60? Well, all I have to do is look at our unit circle. Cosine of 60 is, I do not have the unit circle memorized. 60 is equal to 1/2. I do that. It's equal to 1/2. So it's essentially going to be 1 times 1 times 1/2, and that's going to come out to be 1/2. And if we use that one law that kind of combines sine if we use that one law that says that A is equal to B, B equal to C, and B equal to C, oh, this is equal to B dot U dot V. And so the first answer, the answer to U V equal to 1. And if we do the same thing, 120, 1 magnitude 1 plus magnitude 1 because of unit vectors times cosine of 120 is equal to -1/2. Okay, just move the over. We just move to the next one. So the answer is -1/2. That is equal to E dot W. Easy as pie. Yeah. So let's move on to the next problem. I think I have time. Hope the audio isn't super screwed up because my AirPods died. Um, but actually, I'm gonna plug them in real quick. Next, we're going to be finding the angle between two vectors. So this one's going to be interesting. We're going to have the ability to look at components and see how to break them down. And again, it all comes back to this to this to this formula and how you can plug the numbers in. I'd say this is pretty similar to a physics class in the sense that all you have to do is combine the numbers and boom, it's super easy. Or no, plug the numbers into the equation. It's as easy as that. I can understand it better. I'm not at that point yet. So vector u is equal to 2 comma. Let me double check that. Yes, 2, 4. And v is equal to 6. So v minus 6, 1. So once we have those two there, we have to find um, a few things. We have to figure out the magnitudes. So um, if we're going to plug them into the equation, so 6, the magnitudes of each of these is, as you remember, just the distance formula. So square root of, so 2 squared plus 4 squared is equal to 20. No, that's 4 plus 16, root of 20, and that's 2 roots of 5. So 2 root of 5, v is 37. Root of 37. It's not, that's not very clean. But that's magnitude anyways. So now that we have those, we can find out. So 2 times 6, we're going to go through this again. 2 times 6, the both of the x values 12, plus 4 times 1, the y value is equal to 16. So if we're going to take the equation, we're going to have dot product on top, which is 16, and that's going to be divided by 2 root 5 times root 37. Which just got interesting. So one thing we can do right off the bat is we can 16 by 2 top, but 5 times 37 is 185, which does not have any factors besides 5 and 37. So it's just going to be 8 root 135. Now we're not done. We still have to find the angle between the two of them. So what we've done is essentially simplify the equation. Cosine theta is still floating around. So what is cosine theta? Well, it's just theta is equal to cosine -1 of 8 over root 35. Okay, back myself in the right. I don't know how to get theta. So what are we going to do? We're going to turn to our hand. Oh, the answer is that. I was correct. The answer is theta is equal to cosine negative and a over 135, if you want to make it pretty, 8 over 135. It's and this is about as pretty as it's going to get because if you go any less pretty, it's just decimals. When you go past the cosine negative 1, it's x. So I hope that makes sense. Well, the second time we do it, because it took me like 3 hours first. Now this yesterday. So next problem. Oh, let's go. Next problem. The scalar and vector projections of B on the A. Okay, so this is one that stumped me for a while because our Shasta did not go over it at all, but I know how to do it. So A is equal to component 5, 12, no, 5, 12, and B is 230. So do you remember how to do the projections? So essentially it's this equation, but the one that you're projecting onto the other, move to the other side of the equation. So we're projecting B onto A, so we're going to get B cosine. Essentially going to be B
cosine theta is equal to A dot B over A. Check that. Yeah. So the general rule is the one that you are projecting is the one that gets removed from the denominator. If you want to think about it this way, you say, I'm projecting it, so I'm just kicking it out of the denominator. I'm projecting it out of the denominator. That's just the way to think of it, so you can remember. Because I always get mixed up. Anyways, what is A dot B? Let's start. So A dot B is going to be 10 plus 36. And I hope you remember how to get that. And that's going to be over magnitude of 25 plus 144 is going to be 169. That's 13. I did not do that. Just kind of have it because I thought it was a fun number to get. Anyways, so 46 over 13 is going to be our lucky number for today. That's going to be our scale projection. 46 over 13. Let's double check that. I was wrong. Where did I go wrong? Okay, so I found my error. It was actually not my math. It was me reading off the screen horribly. Should have checked closer. So my problem here is literally it's not 512 component 512. It is component negative 512. Just goes to show how tiny mistakes can screw that up. For the sake of brevity, this is going to result in 26 over 13. That's the equation. And then we're going to multiply that by dot product 2 dot product B. Wait, no, I'm already lost. Okay, looks like we're gonna have to do this the right way. I hope this doesn't bore you too much. I'll just pause these up. Okay, it's been like 10 seconds and I already did it. So you get the dot product on top, you get the magnitude on the bottom, you simplify it, and you get your answer. The answer is 2. So math is great. I mean, guys, read closely because that's what I did. So on the next problem, oh yeah, the vector projection. So the vector projection be on the A. So already the scalar projection, you have to use the scalar projection that you start with to continue on to get to your vector projection. So you're going to vector project B on the A, which means you're going to have to do that answer looks really loud. Give me a second. Okay, 10 seconds later, with scalar vector projections, I was correct when I said that you have to take the magnitude multiply on the vector, but it's not the vector, it's the unit vector. That's why I mixed up. So the unit vector of A. So I already have this, which is our scalar projection, and we're going to have to do it by whatever is going to be inside these components. And this component is going to be the unit vector of negative 5. So we already know what the magnitude is. The unit vector is just the vector component. No, the component over the magnitude. So it's going to be negative 5 over 13, comma 12 over 13. Boom. You're going to multiply it by 2, so it's negative 10 over 13, comma 24 over 13. And there you have it. I'm doing pretty decently. Just making a few little mix-ups in there. I should slow down so you can understand it later because I'm going fast because I don't want the video to be super long. Anyways, let's move on to the next one. Find A dot B. Okay, so we're back to the equation. This one's big. Sorry for the cheer notes. Fun stuff. How are they? Like having friends, better than math. Couldn't say the same. Okay, so let's consider what we have. We have the magnet. We're going to find A dot B, and we have the magnitude of A, we have the magnitude of B, and we have, so what are these? A little closer this time. Look at my white eyes. 8, 6, respectively. 8, 6, 30. So let's just go back to the equation. So if we want to find A dot B, it's just going to be the magnitude 8, 6, cosine 30 equal to A dot B, which is our answer. So let's think back to the unit circle. What is cosine 30? I'll go back to the unit circle and tell you all the answer. The unit circle, cosine of 30 is equal to root 3 over 2. So if you look up the unit circle, you can actually see that the y value of the coordinate on the unit circle where 30 degrees is the cosine. Meanwhile, the x value is the sine. Hold on, did I just get the mixed up? Pause that. Okay, I was correct. You grab the x value of the coordinate. So we're gonna move this back. I got such a percent off. The value was root 3 over 2 is equal to cosine 30. So root 3 over 2, which is just going to be 48 times 2, which we can simplify 24. Root 3 and boom. All right. That's easy because this is equal to A dot B. Make sense? Okay, now we're going to go to our last one. And this covers something that I actually didn't go over, which is nothing more than a notation for a unit vector. I'm pretty sure it's a unit vector. If anything, it's just a vector. Yeah, it's not a unit vector, it's just a vector. So here's another way to write a vector. And the way our teacher explained this made no sense. The way I explained it made no sense. You know, anyways, this, if you have a vector, let's say vector 8, comma, 21. Belongs 21. Anyways, if you want to rewrite this in terms of how far you're moving on the axes, you can actually just say 8i plus 21j. And if you're going to go into a z coordinate, it's going to be k. So 0k. Just forget about this one. Anyways, this is just a simple way to say 8x plus 2y. Problem is, if you say x, you're in a function and you're not in a vector. It's just because the notation for functions is different. Like, ax plus by equals c. So this is the standard form for an equation. I'm pretty sure it's a standard form of something. But this goes into like algebra, and if you use x right here in the component, then all of a sudden it's like, wait a minute, 8x and 21y. Is this an equation or a component? So you can see where you get confused. But where you could get confused if we didn't use I, J, and K. And that's literally what I, J, it's just essentially saying, hey guys, we're going to move 8 units on the x-axis and 21 units on the y-axis, just so everybody's chill with that. That's essentially what it is. So we're given a problem, which is the last one, and it's a real world one, is find the work in J done by force 6i plus, no, minus 4j plus 9k. A few other numbers that we have, that moves an object from point 066 to point 61418 along a straight line. The distance is measured in meters and the force is in newtons. So what can we get from this? All it gives us is a vector. and it's telling us. I could have sworn there was more data. It said 30 degrees. Uh, oh yeah, we have to extrapolate that. It's essentially saying what's going on. So you can find the answer to this by just plugging everything in. But we are now working in 3 dimensions instead of just 2 dimensions. So first we have to find magnitude. Magnitude is going to be this, all of them squared, and then the square root of them at the other. So 36 plus 16 plus 81. Root of that. Yeah, the Pythagorean theorem does extend into the three whatever's 3 dimensions. 36 plus 16 plus 81. Root of 133. I'm pretty sure that's correct. Let me work this out before I actually show it to you. All right, guys. So it turns out I was totally wrong. I did not remember how to do this one at all. But it is interesting. It covers a new topic that actually didn't get taught. It's just kind of its own thing. I would make a new video for this, but I'm already on this video. It's a problem. So what this does is it works with something called a displacement. This is not works with something called the displacement vector. And the displacement vector is essentially a vector that's saying, hey, what if we went along and we met at a 90-degree angle? So yeah, so we're going to start with this. We have the actual vector that they gave us is 6, 4, 9. First, the problem is 6, 4, 9, to be positive. Yeah, -4. And so now what we need to do is to calculate force versus direction. We need another vector to compare it with. So if we're on here, this one's going up. That's where our vector is. But we don't have anything to compare it against. What we're going to do is we're going to try and draw a vector. What is that vector? This. Well, so I would note that the point at which this vector ends is going to be where it makes a 90-degree with our first vector. And this is called the displacement vector, if I remember correctly, if that's what this says. The displacement vector. Yep, the displacement vector. You can read about this in the textbook, but it really doesn't explain very well, to be honest. The textbook just kind of leaves you to flounder. So yeah, the displacement vector is something you find using the initial point and the final point. So our initial point is going to be 0, 6, 6. These are not components of vectors. These are just coordinates. That's the word. And then we got 6, 14, 18. So how do you find this displacement vector? I mean, the word displacement is just how this is essentially like a change in the vector. So it's the way you would calculate slope, almost. So the displacement vector is going to be, let me confirm this. Yeah, it's just going to be the y2 minus x2 minus x1 y2 as well. So 6, we're going to get 8, and we're going to get 2. So this is our new vector. It's that one. So one would argue, and this is what I actually thought started. Uh, the reason I got confused is because of this assumption is that this one goes along here. So 0 to 6, 6 to 14, 6 to 18, and that's just this increase line. 6, -4, obviously 6 to 14 not a jump, -4. Neither is 6 plus 9 equal to 18. It's essentially saying that we have a vector that's moving at this force, and this is the direction. So if you have your box, it's like the box ended up moving here, but the vector was pulled here. So why did it end up here when it was going here? That's because the visible vector, the displacement vector, which I would think would be like, but that's what this displacement vector. This is what was supposed to happen. This is what ended up happening. So what's the other vector? The other force that's working out. And that d, that's going to be the in our equation equals force times distance. That's going to be our distance. This makes so much more sense now. So this is what we're moving. Displacement is like moved. Um, yeah, this makes so much more sense now. Let me retry so I can do that. I'll do this. So we got a thing, and it's got a force acting on it. That one. And that one is 6 negative 1. This would be the ideal, except that's not what happened. Box ended up getting moved from here to here. That wasn't expected. So what's the actual amount of work? Because there was a distance. There was a distance because that was the actual vector went this way. And we have to find that vector based on what actually happened. And yeah, and then we just calculate it. So work is equal to force as times distance, but because we're working with vectors, it's not multiplication anymore. Now it's a dot product. So we're going to dot product this bad boy with because this is our force and this is our displacement vector or the distance that we actually check. So what is it going to be? It's going to be 6 times 6 is 36. You know how to do it? It's the same thing in coordinates, is multiply each respective axis value and add them together. So 6 times 6 minus 32. Something. Plus 18. That took a long turn. Oh, yeah. So our actual vector is. Where did the 9 come from? Oh, yeah, I did some math. This 6 is 18. This must be a. This 2 is a 12. Because it's not 8 minus 6, it's 18 minus 6. So it ends up being 12. Always take care of your math. That's what it was. So I for a second thought I was completely wrong on my other observation, but I was not. So we're just gonna do 12 times 9. What's that? 12 times 9? 108. So 36 minus 32 is 4, plus 108 is 112. Easy, easy as pie. Work is measured in joules, so we're just going to put in J. There we go. So you need those 3 components. I hope that makes sense. Like you have a force, and then you have like where it actually went, and so you have to figure out. Let's figure out what our displacement is. Hope that makes sense. We have one more problem because I've been standing here watching dinner. I was before I started the video, I was gonna wait a bit, and because it was still really early and I'd eaten kind of late, and now I don't eat dinner. I'll just go out and get some fast food. Next problem. Where you go? So this one is kind of the same concept, or mixed with it. Like we're still in work. I'll move this one though. Resize it. Okay. So this is question number 9. A tow truck dragged a stalled car. Where the chain makes an angle of 30 degrees per hour. The tension in the chain is 1100 newtons. How much work is done by the truck pulling the car? 1 kilometer. So here's our truck box. We got 1100 newtons. This is essentially our vector. This is a magnitude. It has gone 1,000 meters. I'm going to just convert it right now. Because I did not convert the kilometer to meters. I just got 1,000 meters. This is a 30-degree angle. So how much work is done by the truck in pulling the car 1 kilometer? So let me check my notes just real quick. And there they go. Oh yeah. So you just have to multiply by the. So we already have our formula right here. Magnitude, magnitude. We have two magnitudes right here. So it's already set. I think this is actually a really good tip. Recognize what types of variables you have, what you have. So 1,100, that's scale. That's going to be a magnitude because it's going somewhere. Because it's at 30 degrees, so I already know what it is. That's a very good tip. Identify your directions. Or identify what type of number or what type of thing that number is. So we're going to take our formula. We got 1,100 times 1,000 times cosine of theta, and that's going to give us a result. But why is this correct? Remember, it's force as a function of distance, and our distance is 1,000, and the one is 100. And so if we were in a different setting, these two would be vector components. And so essentially you would be doing would be taking the dot product of your force and your distance. This is how far actually this would work. Well, it's force times distance, that's our force, times our distance, we multiply them together, times that, and you get the dot product, which is equal to force times dot product. F dot product B, that makes sense. So I just put that in the calculator. Cosine of 30, let's go back to the unit circle. I really need to memorize that thing because that's what I realized a few days ago. Cosine of 30 is root 3 over 2. Root 3 over 2. So it's essentially going to be 1, 2, 3. And that's going to give us, let's put that 550,000. But the truth is, we don't measure our whatever they are, our work in roots. So what we have to do is we have to multiply that times root 3. So, well, we actually have to multiply 500 times root of 3. And that's going to be this funny looking number. It's an autistic number, actually. That's what Trump was saying. 952,627.9. Pretty sure it's joules. Yep, it's joules. And boom, that's your solution. You just have to identify what you already have and slap it into the equation. I would draw your attention to this is like a simpler version of the problem we just did just now. It's like imagine you have a vector here. This is a component vector. X, Y, Z, that's the force getting exerted. And then you have your distance is coordinate X, Y, Z all the way to coordinate X, Y, Z. And you're like, dang, how do I solve this? It's gonna be just finding your component, or yeah, finding a component vector with these two coordinates. And then that one. And I'd love to say dot product. I think that's wrong. Yeah, you have to do a bit more. Anyways, you can figure that out. I'm sure. I'm sure you'll get it. Oh yeah, it is. Yeah, it's just finding the vector here. Averages or something. It's just find the component vector of this dot product. It's just dot product, and then you have your answer, which is your word because it's your force times your distance. Because this one, it doesn't have to be flat. It's just wherever it actually went, like real expected versus reality is kind of. Anyways, I hope that was productive for you because it was productive for me. Now I'm going to go overload on my calories and cheat a bit. And yeah, I'll see you next time.